Hello everyone and welcome back to our Australian Geometric PDE seminar series. I hope you've all had a pleasant Easter. I understand that school holidays and certainly teaching at some universities is not happening at the moment, so people might be looking after little ones. But for those of us who managed to make it, thanks for coming. We've got Adam Thompson from UQ who's going to continue talking to us about mean curvature flow. I understand that Adam's going to talk to us about continue talking to us about convexity, preservation of convexity under the mean curvature flow, as well as Huisken's convergence theorem. Thanks, Adam.
Thanks, Tim. Thanks for letting me talk again. Yeah, like Tim said, so today my plan is mainly to talk about Huisken's convergence theorem. So what happens if we start with a really nice initial condition, if we assume our initial hypersurface is convex. To talk about that, I'm going to first talk about the fact that convexity is preserved under the flow. I guess if it wasn't preserved, it doesn't make sense to try prove a theorem like the one Huisken did. Yeah, so I'll get into that. So as similar to last time, just remind everyone, I'm going to take Mn to be closed, bold, and I'm going to get some initial data, just embedding this into Rn plus 1. Rn plus 1, and then a family of embeddings. So of course, same as last time, it moves by mean curvature flow if it solves our mean curvature flow equation. I'm just gonna write MCF every time. Yes. Marshall. X equals F naught. So we have this initial value problem. And then last week, what I spoke about is the fact that given this initial data, we can get a unique maximal solution that's characterized by the curvature, our second fundamental form, blowing up at the maximal time. So given F naught as above, there's a unique mean curvature flow here. 2, 1. And we have M sup T A equals plus infinity. Okay, yeah, so like I said earlier, this week I want to talk about the case this week. Want to talk about what if M naught is convex. Okay, and I'll define that just in a moment. Yeah, and we're going to see that in the case that it is convex, that we can say a little bit more than we did last time. So of course, because we're starting with a compact surface, our avoidance principle is going to force singularity, but we have good information about the singularity. Okay, so the singularity is going to have to be a point. Our surface is going to have to shrink to a point. Yeah, so I'll get into that and I'll draw a picture in just a second. First, let's say convex. So by convex, I mean, so Aij is positive definite at each point. So maybe I should have said for all x in M naught, my second fundamental form is positive definite. If I let, so maybe I'll order these. So lambda 1. If I take my principal curvatures at a point X in M naught, I could also phrase this right as each one of these is positive. Yeah. And so we could also talk about mean convexity. I'll just write that down for posterity. So it's mean convex if the mean curvature is positive. Again, this is for all X in M naught. And there's some kind of intermediate convexities, which I might write down at some point in just a remark, but we're not going to focus on that so much today. Today, I'm going to be particularly focused just on this positivity or positive definiteness of the second fundamental form. Although I do want to observe that convex implies mean convex. Of course, if a bilinear form has positive eigenvalues, then its trace is going to be positive. And just some examples, right? So an example, maybe the easiest example that comes to mind of a convex surface is our sphere. Although the ellipsoid is also convex. Yeah, so here with the sphere, or Sn, are all the principal curvatures are 1 on R, which are bigger than 0. And in fact, they're all the same, right? And so part of the reason why I mentioned the sphere here is that we're going to see that for a convex hypersurface, when we run it under mean curvature flow, after a long amount of time, our hypersurfaces are going to start looking more and more like spheres. Okay, so our eigenvalues of the second fundamental form are going to become more and more uniform. Okay, so my first task, though, that I got to focus on is task show convexity is preserved. Yes, preserved. And then after that, kind of, I guess, the main part or the main thing I want to get at today is my second task. And this is going to be Huisken's theorem. So I'm just going to write that down now so that we know kind of where we're headed, what we're working towards. Okay, so in n greater than or equal to 2, if I take a uniformly convex initial condition, convex, then what do I have? So I run my mean curvature flow. Solution on 0t converges to a point. And if we renormalize to get, so if we renormalize because our mean curvature flow is going to contract our hypersurface down, we're going to try renormalize to see what kind of geometry we're approaching. So if we do this so that my volume, so my renormalized mean curvature flows, I'm always just going to put a tilde on top. I do this to keep the volume constant. then what do I get? Then this new one exists. We'll see it satisfies a slightly different equation, but it exists for all positive times, and it converges to a sphere, in the C infinity. Okay. Yeah, so sometimes I'll just point out, some people phrase this as the fact that these, as my hypersurface under mean curvature flow shrinks to a round point, they say sometimes. So it's shrinking to a point, but it's getting very round. It's getting round as it goes there. It's starting to look more and more like a sphere. And just to make some remarks, okay, so remark. One, the convergence is actually very quick. So convergence is exponential in any of the CK norms. CK norm. Secondly,
Adam,
yep.
What do you mean by exponential? Because there's two different times, right?
Exponential, I believe, in my new time. Yeah, so
Okay,
perhaps on here,
time.
I should have reparameterized this with a tau or a t tilde, I think Huisken does, but I'm not sure I'll be able to write the t tildes neat enough. Yeah, in the new time. Okay, then secondly, I wanted to point out,
I guess it doesn't make sense to talk about exponential convergence if you're on a finite time interval, presumably.
Yeah, there's a particularly natural new time variable that Huisken uses, and it's exponential with respect to that. So, yeah, it's a good question.
You can always think. I mean, when you define type 1, you say curvature is inverse linear. What do you mean by linear? Well, you look at the remaining types. You can always do that. But yeah, it's clear that it's with respect to the new time representation.
Yeah, this is the new time. So yeah, I just wanted as well to point out explicitly that this is part of it that I missed when I first heard of this theorem, that this is ruling out behavior like the neck pinch that I mentioned last week. So when we're shrinking to a singularity, we're doing that in a way that the entire shape or the entire hypersurface is shrinking down to a single point, right? Okay, so yeah, perhaps I won't write that down. So second as well, the n equals 1 case, the reason that's not in the theorem, this is was proven around the same time, I believe, by Gage Hamilton. Yep, so we get something similar happening there. Yeah, the reason it's n greater than or equal to 2 in Huisken's theorem isn't because it's false in n equals 1, it's because someone else proved it. Okay, and then, yeah, okay, yeah, that is all I had to say there. So I'll just move on now to my first part. Yeah. Part 1, my preservation. Yeah, so I mean, we've done quite a bit of kind of trying to preserve certain quantities already, or controlling quantities, perhaps. So this preservation of convexity, I'm going to go through quite quickly, and I'm not going to write the proofs explicitly because it's going to come down to the maximum principle. So the main kind of machinery for this part that we're going to use is a tensor maximum principle. And this is due to Hamilton. Okay. So suppose that I have on some time interval that I have a tensor quantity which evolves in a certain way. So this is going to be with respect to my metric at time t. This is under some kind of curvature flow, presumably, or at least some kind of evolving metric. So I have xk. So all these covariant derivatives are with respect to the metric at time t, and nij, where x is a vector field. Actually, I should say it's vector field. The reason I crossed out what I was doing there is because x can possibly depend on time. And so this n is polynomial in my m's and also my metric, and satisfies something called the null eigenvector hypothesis, or condition. For some reason in my mind, I keep saying hypothesis, condition. Okay. So I'll say my conclusion first, and then I'll say what I mean by this null eigenvector condition. So if, I'm sure many people can guess the conclusion, if this is positive definite at t equals 0, then positive semi-definite, then this continues to hold for all t, where my flow continues to exist. Okay, and so this null eigenvector condition, what that means is that if I have a null eigenvector of m, then when I put that eigenvector into n, it's positive. Okay. Okay, so I'm not actually gonna prove this tensor maximum principle. I think like the proof is fairly similar to your scalar maximum principle in format. You look at the first time that, or you assume for a contradiction that it's violated at some point. You say at one time I have a vector that violates it, and then we go through and we look for some contradiction, you know, something that breaks this equation here. Yeah. Okay. And so now the preservation of my second fundamental form is going to follow pretty quickly. So this implies convexities preserved. So preservation of Aij greater than follows, since when we looked at our evolution earlier in the seminar, we get Aij plus a squared Aij minus 2 J. And so this is going to be my n. And it's fairly quick and easy to check that this n does indeed satisfy the null eigenvector condition. Okay, and so I get immediately that if Aij is greater than or equal to 0, then that continues to hold. But in fact, something slightly nicer, something slightly stronger continues to hold as well. Okay, so something stronger holds. And that's this. So I'll put this in a proper little environment down here. So assume at the beginning of my mean curvature flow, I have this inequality. So not only is my second fundamental form greater than or equal to 0 or greater than 0, it's greater than or equal to some positive multiple of the metric, or some positive multiple times the mean curvature times the metric. And I'll put an upper bound too. J holds on M naught, where C eta 0, and this is going to continue to hold as well. So this holds for all t such that my mean curvature flow continues to exist. Okay, and so again, this is going to use the 10 to maximum principle. I won't go through and prove it in detail, but I'll just write out. So the M we use is this minus epsilon Gij. My vector field X has these components, so 2 on H, GKL. And my Nij again is similar. Okay, and we could compute that M satisfies the relevant evolution equation just from our evolution equations we've previously looked at. So I'm not sure. I don't think going through those again in painstaking detail will add much. And so really here, the great thing about this equation is I'm just going to notice that since my hypersurface or my initial hypersurface is compact, this assumption I put on the second fundamental form being convex, being positive definite, is actually going to give me this initial inequality that I wanted. So just assuming that Aij is strictly greater than 0 because of compactness, we get this lower bound. So okay, greater than 0 on M naught implies that for some epsilon, I have this Gij on M naught. And then of course, from what I've said above, I then have that holding along my mean curvature flow. Yeah. Okay. So yeah, that's, I guess, all there is to the preservation of convexity. You can also talk about like these intermediate convexities. So just remark if, so for P or X in M, maybe I'll just call it, look M naught. If lambda 1, lambda 2, if these are my principal curvatures, are the principal curvatures, we can talk about M being, so call naught beta convex. If actually maybe for some reason I've written beta convex there, it feels like it should be K convex. I'm not sure if when I was reading that and when I wrote that down, I was just having a kind of moment. Okay, question mark. But this is also preserved. I'm not actually going to look at this, but I thought I should point it out. This is also preserved under the flow. Yeah.
Adam, quick question. The upper bound, is it a similar computation with the maximum principle?
I believe so.
That's a little bit surprising, right? Because it seems that you're gonna get the wrong sign if you, but yeah. I don't know. Maybe
Yeah.
I'm thinking, scalar curvature for Ricci flow. I mean, it works in one way, but not in the other, right? But,
Okay. Yeah. So okay. So part 2. So now that I
Sorry,
actually
Adam,
know,
just a quick
if I
question.
start- yeah.
Sorry. So are
Yeah, go
these principal curvatures, they're ordered, like smallest to largest?
Yeah.
Okay.
Yeah. So I've ordered those.
Oh yeah, sorry, I missed
Smallest to
that.
largest.
Cool.
Yeah, no problem.
Thanks.
Otherwise, I guess it'd be a little bit arbitrary.
Yeah.
Just try to pick.
I thought it was like for any K or something, but that's a bit weird. Anyway, thanks.
No trouble.
it's equivalent for any case.
Good point. Yeah.
Okay. Yeah. So now let's get on to the main meat. So again, what do we want to look at? So if we start with something uniformly convex, then as I said before, a mean curvature. So this original mean curvature necessarily only exists for a finite amount of time. It has to come across some kind of singularity. But this singularity is, I guess, in some sense, as nice as possible. It's going to converge to a point. And if we renormalize, if we so that my volume is constant. And my tail. Then yeah, then this. Then my new renormalized flow exists. Positive times and converges to a sphere. Okay, and so I'll point out now that I have about 20 minutes left. So if someone was hoping to see a full proof with all of the precise details, unfortunately, I'm not going to be giving that. So what I'm going to give in these kind of remaining 20 minutes is essentially a brief explanation of the last few sections of Huisken's paper. So a lot of the kind of integral estimates that I use come from earlier in the paper. I'm just going to outline how that's all put together and explain, I guess, why that gives us this convergence to a sphere. It's not going to be a precise and rigorous kind of mathematical talk with all of the estimates in. Okay, and so an important part of what's going to happen here is that we're going to look at this renormalized flow. So in fact, these renormalized mean curvature flows also satisfy an equation, and it looks like this. So partial, the derivative with respect to a different time variable, what's x, is equal to minus tau x plus, and I get this factor coming out that I add on, and this is, I guess, the factor which keeps the volume positive. So this is defined by this function h is the average of the square of the mean curvature. Tau d u tau. Okay. So where does this come from, right? This equation, I'm going to observe that if I have a solution of my mean curvature flow, if T solves mean curvature flow, and I'm going to take some function phi that I'm going to use to normalize it to R plus, such that when I look at the volume, sorry, I should put a T in here. T. Okay. And then so I could pull this phi out of my volume, of course. And because I'm in n dimensions, or because I'm looking at an n-dimensional volume, it's going to gain this factor of n. And if I went through that, I could get some differential equations going. And eventually, so it's going to tell me that the way phi should evolve is it should evolve according to this equation. And then if I plug, so if I plug this in to an equation like this, and differentiate using my product rule, what am I going to get? I get h n f plus phi h. So again, when I put a tilde, that's the normalized quantity, and this is without the tilde is the unnormalized. By this I mean this is going to be my eventual f tilde. And then the way that my mean curvature flow, and also this f, this h, are going to scale, I'm going to end up with the fact that this is precisely this equation I wrote above. I'm sorry, this is a h with a, should be a normal vector here. Plus f tilde with this phi squared coming out the front, and that's where my new time variable comes from. So I'm going to define tau of t to be the integral of this squared, and this gives me that new equation. So with respect to this variable, I'm going to get this nice evolution. Sorry, there should be a line. So yeah, that's roughly, that's where this different equation comes from. Now, my first step, so I guess now I'm going to talk a bit about the proof of Huisken's theorem. So step one is going to be looking at the way these singularities can form. Okay, so basically I want to rule out this kind of neck pinching. I want to look at the part of the theorem that says that my hypersurfaces are going to shrink to a single point. And so for this, notice, so I kind of notice the different behaviors. So in a sphere, my mean curvature, it's constant everywhere. So in particular, my max of the mean curvature is equal to the min of the mean curvature. And secondly, keeping in mind that we want to show at some point that our surfaces converge in some sense to a sphere, maybe even after renormalizing, we're going to want as well the mean curvatures, or the max and the mean curvature, their ratio to go to 1, because that is what's true on a sphere. So before I do that, I'm going to just contrast this with this neck behavior, in that if I just have a neck pinching off, if I look at my curvature where the singularity is forming, this is going to eventually be much bigger than the min. If I looked at, you know, some curvature happening in a place where nothing's going wrong. So if I'm trying to rule that out, I want to say that when my maximum of the mean curvature is getting really big, my minimum's coming with it. I can't just send the maximum mean curvature off to infinity and keep my minimum mean curvature bounded. In fact, the way what Huisken shows is, so we want to show that this ratio, and so right now we're still just working with the unnormalized flow, that this approaches to 1 as we go to this maximal time. Okay, and an important observation.
Hey, Adam.
For this, yep.
I just thought you might want to clarify if your little picture up there is supposed to be concave or convex.
Yeah, so sorry. I guess the picture here is not necessarily convex, because I'm trying to say that in the convex case, I can't have something like this happening. Yeah, so I mean, I guess the easiest picture I could come up with, yeah, is not convex.
Yeah. Okay. Yeah.
Yeah. Yeah, sorry, I should have mentioned that. Yeah, I'm not meaning to claim that kind of dumbbell shape is a convex hypersurface.
Yeah, I figured I'd just it's all good. It's all
yeah,
good.
no, it's thanks. Okay, important observation is that so as part of this proof, part of the proof, and this is proven, this inequality that we saw we had before, and that's preserved along the mean curvature flow, actually implies as well an inequality for the Ricci curvature by using something, by using the Gauss-Codazzi equations or something. So my Ricci curvature is actually bounded below by the metric. And so Meyer's theorem, or Binet-Meyer's, is going to give me some bound on the diameter of my M, of my MT. So C just being some constant, I can show that this is bounded by the minimum of the mean curvature. So Binet-Meyer's says that if we have an inequality of this form, so Ricci curvature being greater than or equal to K times the metric, some constant K bigger than 0, then our manifold is compact, finite fundamental group, and also that we get a bound on the diameter of the manifold in terms of K. And I'm also getting that this is going to go to 0 as T approaches the maximal time due to this inequality above. Okay, so when we do show that the max and the min of the mean curvature, when their ratio goes to 1, as we approach the maximal time, this does actually give us that the diameter is also shrinking to 0. And so our hypersurface is going to contract to a point as we want it to. So this does work very nicely. Okay, so in the second step of Huisken's theorem, he starts to look at this normalized equation. So normalized equation. Okay, and so in particular, when we start looking at this normalized equation, we've come up with a load of nice inequalities and this nice limit up here that we also want to use now we've normalized. So in fact, the comment that I have to make here is that these are going to continue. These are also true under this new normalized one. H max, H min is going to approach 1. And I'm sorry, we also have this, which I had not written before. So they're approaching 1 on n as tau goes to capital T tilde. Okay, so a priori, I guess when I change my time variable, it doesn't necessarily have to be defined on 0 infinity. That's something that comes as part of the proof. And so the reason that this is true, that we get these almost for free, is because these were all defined, I guess, geometrically, and so they all scale correctly. So when I scale my hypersurface by this phi, the left-hand side and the right-hand side scale in the same way, scale to the same power, and so the inequality holding for the unnormalized flow automatically just passes over to my normalized flow and continues to hold. Okay, and now from here, so for the normalized flow, what we find is, so before in the unnormalized flow, mean curvature was blowing up because the curvature was, but this was actually just because we were shrinking to a point. Okay, so there was no part of the curvature that was kind of blowing up much quicker than the others. So now that we've normalized, I'm actually going to get that these new mean curvatures are bounded. So they're bounded away from 0 and they're bounded above by some finite constant as well. Okay, and using this, using the fact that these are bounded, I can look at the integral of this h squared, so that I defined before. H, and this Huisken shows at some point that this isn't finite, so this is infinite for the unnormalized flow, but I have that this I can now say is bounded. So if I'm integrating something continuous over a bounded domain and it's bounded, everything's going to be bounded. So the fact that my integral diverges tells me actually this maximal time must have been plus infinity all along. Okay, and then, so the final step that Huisken goes through is the actual convergence, so convergence to a sphere. Okay, so shows this is kind of the final section of his paper. Show there's delta and C greater than 0, such that so my second fundamental form minus my mean curvature divided by n is less than or equal to the exponential term h max H-min, similar phenomenon. IJ. So equal to. Okay. Yeah, so in the final kind of section, he actually goes through and he uses integral formulas and bounds he's proven earlier in the paper to show that we get this exponential convergence of these key quantities. And then he notes that already from this, so from this, say, third equation, you can see some convergence to a sphere in a kind of weak sense. I mean, heuristically, if you have a hypersurface and at each point all the principal curvatures are the same, then you can prove that if those principal curvatures aren't zero, that you must have kind of part of a sphere. So if it's compact, I guess you get the whole sphere. And then similar to last week, using the bounds and formalizing your argument correctly where you have to, bounds on the curvature gives you curvature of higher derivatives and you get convergence in your C infinity topology. Okay, and then we can see here as well why you get this exponential convergence in all of the finite CK norms. Yeah, so that was kind of about all I wanted to say today. Yeah, unfortunately, I think going through the entire paper with all the details would have taken a very long time. So hopefully got something out of me just talking through it and just kind of seeing the skeleton of the proof. Yeah, and hearing the theorem. Thank you.
Awesome, thanks for that, Adam. Let's thank the speaker for taking us through these fun results.
Thanks, Adam.
Does anyone have anything they'd like to say or a question they have for Adam?
What did you think of Stampacchio iteration?
I didn't look into the Stampacchio iteration this time around. I only have vague memories of last year you mentioning how nasty it was, so I stayed as far away from it.
I spoke very, very fondly of Stampacchio iteration. No, I remember in the summer school we did do it, but it was not accessible.
Yeah, that's
So at some stage, probably one of the talks will have to do that. I guess the asymptotic convexity, for example, would be a natural place to talk about those methods.
I think it's actually like being more serious. I think it's actually something of a fundamental technique that students should be exposed to because it's something like a plan B, a plan C. Like if things don't work out, just figure out what should at least be true and then write it as an integral estimate, and then sort of things, you'll be able to control stuff. Even if worst case scenario happens, you'll be able to compare I think it's a good technique, and the iteration part is really classical. I don't know if anyone wants to talk about it though.
I'd be happy to talk about it. I actually want to talk about it.
Yeah.
Oh, awesome.
Yeah, good
Awesome.
Yeah.
Awesome.
Any further comments or questions?
There's a lot hidden, for example, in this limit of H max on H min going to 1. And that's really where the work comes in. So.
I was going to ask, how does that, is there a monotonicity formula, or is that the tool that you have to use?
That's the hard work. Yeah, that's the Stampacchio iteration and things like that, which give that. Yeah.
Because for Ricci flow, this took 20 years more to prove. So I guess it must be non-trivial for mean curvature flow.
Yeah, it's somehow harder for mean curvature flow than Ricci flow in some ways.
It will come up in asymptotic convexity.
Yeah, that's right. Yeah.
Yeah.
Good.
Anyone else have anything else they'd like to say?
So an alternative, which I'm not sure who's speaking next, but I mean, there are several ways you can prove the Huisken theorem, and one is to go through this integral estimates and so on, the Stampacchio iteration that Huisken did in his paper. But there's some other shortcuts once you have the estimate that you did prove, which is this second fundamental form bigger than epsilon mean curvature times the metric. Then you can sort of get from that to some geometric control and get convergence from there. So it may be a good thing for somebody to talk about that next, possibly as a sort of go through an alternative proof of Huisken's theorem, which avoids that hard machinery. Anyway, we can talk about that.
Yeah, I've given that exact problem to students before. It's like, look up Ben's 93 paper and just do the Huisken's theorem only special case, basically. Yeah, it's much quicker. I'm not sure if that's on the schedule, but we can talk about it.
Yeah.
Well, schedule is certainly flexible.
Yeah.
Right then, let's call it a day. Let's thank Adam again for taking us through those results.
Thanks, Adam.
Cool. I'll stop recording there. Thanks everyone for coming, and see you next time.